have found over the last 100 years that a very fruitful way of thinking about the universe is to allow for the possibility that left, right, back, forth, and up, down, the three dimensions that we all are immersed within, we move through freely in day-to-day life, we have found it useful to imagine that there may be more than those three dimensions of space. And we have found that, at least theoretically, using mathematics, if you engage that possibility of more than three dimensions of space, certain problems in physics all of a sudden admit to a solution. And this is an idea that goes all the way back to the early part of the 20th century, around roughly 1920, when a German mathematician, Theodor Kaluza, was studying Einstein's theory of gravity. It's called the general theory of relativity. And he found, rather surprisingly, that if he imagined applying Einstein's insights not to a universe with three dimensions of space, which is what Einstein had in mind, but to one with four dimensions of space, with time included in both approaches, he found that he could find a framework that put together the laws of gravity and the laws of electromagnetism in one theoretical package. So he found a way of unifying the then known laws of physics. You move through the world and you want to give some information about your location. You have to give a street, a cross street, and a height, a floor number, if you want to meet somebody. That would be the data that you need to give. The ideas of these higher dimensional theories would be that that's not enough information. You have to give those three pieces of information plus more to really nail down where you are. A very natural question when confronted with this strange idea of more than left, right, back, forth, and up, down is, well, we immediately see those three dimensions, why don't we see the others? And this is a real puzzle, it's a real problem that people have come up with very interesting and creative solutions for. If the math of your theory is suggesting more dimensions, but you don't see them, where are they hiding? And one of the places that they may be hiding is in plain sight. It may be that those other dimensions are all around us, just like the three that we know about, but they're tightly curled up to a very, very small size. So tiny that we can't see it with the naked eye or even with our most powerful equipment to date. And often people get a little confused. What do you mean by a small curled up dimension? And all I mean by that is, if you're a little tiny ant and you're walking along one of these tiny dimensions, you circle around back to your starting point very quickly. You can't go very far in that dimension because it curls back in on itself, like a sphere or like a little tiny circle. And you go around it and you come back to your starting point. And if that circle or that sphere is so tiny that we don't have the visual acuity to pick it out, those dimensions can be all around us and yet be invisible. So according to these ideas, if I take my hand and I sweep it in front of my face, I wouldn't just be moving in the obvious dimensions that we can all see with the naked eye. I'd also be, in some sense, moving around those other tiny dimensions. I'd just be returning to my starting point over and over again so quickly that on average, I wouldn't even have recognized that I took the journey at all. To me, the most exciting thing that one can do with one's life, really, is try to get some sense of how we got here. Where did the universe come from? Where did life come from? Where does consciousness come from? These are the big questions that frame existence. And what we are doing in physics, and in string theory in particular, is trying to answer one of those. The real motivation, the driving force behind what we do, behind these ideas of extra dimensions and strings and quantum mechanics and general relativity, we're all trying to figure out where the universe came from. And the current laws of physics, remarkably, take us back to a fraction of a second after the beginning. But the current laws break down. So we are really working hard to find laws that don't break down under any circumstance, no matter how extreme. The early universe was very hot, it was very dense, it was very a violent arena. We want laws that can cope with that arena, allowing us to peer back using mathematics and understand what happened at time zero. That, to me, would be a remarkable achievement if our species can get to the point where we can say, here's how the universe began, here's why there's a universe at all. the notion of before the Big Bang could be a meaningless question. It could be that time comes into existence with the bang itself, and asking questions what happened before doesn't make sense because the notion of before doesn't apply. That is certainly a possibility, but I am certainly open to other possibilities. For instance, some of the theories that we're working on today suggest that the Big Bang was not the actual beginning of the universe in the grandest sense of the term, but rather was an interesting event that gave rise to our part of the big cosmos. But there could be other Big Bangs happening here, there, other far-flung places throughout space. So the Big Bang may simply be an interesting event, but not the starting event. So the notion of what happened before it may be perfectly well defined, and using our mathematics, we may even be able to describe what it was like in those pre-Big Bang eras, those pre-Big Bang arenas. Will we ever observationally be able to probe those realms if they exist? Maybe not. Probably not. But I don't think that's any cause to say that it's not in the realm of science, or it's not worth studying or thinking about. Because one of the key things that's often lost is, when you're testing a theory, you don't need to test every single prediction of the theory. You need to test enough of the predictions that you gain confidence that the theory is a good guide to the nature of reality. And then if that theory tells you things about realms that you can't see, like a realm before the Big Bang, you're actually learning about that realm, even though you can't test it or see it. These kinds of ideas are really helping us gain the deepest insight into the very nature of reality. And I don't know how long it takes, 100 years, 1,000 years, whatever, when our picture of reality shifts, when we thought there were 3 dimensions and there are more, or when we thought that time was universal and we learned that it isn't, or when we learn that space is flexible as opposed to the previous Newtonian version of it being this unchanging stage. These shifts in our basic understanding of reality do begin to infiltrate the way we think of ourselves and the way we picture how we fit in to the grand scheme of the cosmos.